have been talking about curves so far, right? So today we are going to start on surfaces. So as far as the motivation or requirement of studying surfaces is, I suppose, quite obvious, because for most of the objects you would like to have the representation of the surface by which you can observe the shape of the object, right. So surfaces are basically nothing but some sort of a boundary representation of a 3D object, right. So we are going to look at the various methods of generating these surfaces. So as I said, these surfaces are primarily the boundary representation of these objects, and as in the case of curves, we desired the curves to be having the properties of being smooth, right. For instance, just a polyline representation of a curve shape is not adequate in all situations, right. Therefore, we looked at the various representations and methods of generating smooth curves. So similarly, here also what we would like to study are the generation of these smooth surfaces, right. So as in the case of curves, there are various representations. The two major representations are implicit representation, where you have the representation of the surface as some function x f x y z equals to 0. So there is an inherent solution of a system of equation to be able to get the surface, right. So for instance, a plane is a x plus b y plus c z plus d equals to 0 is in its implicit form, right. And you also have general quadrics in implicit forms, right. Ellipsoids, paraboloids, they are the special cases of that quadric. And then we also have parametric representation, right. So in parametric representation, each coordinate x, y, z is represented in terms of the parameters. So in case of curves, we had a single parameter to be defined, right. So here we have the two parameters which defines basically the domain of the parameter, right. So for instance, if I want to define a parametric surface in a domain, a rectilinear domain, u ranging from 0 to 1, v ranging from 0 to 1, a surface of this kind can be constructed, right. So again, there are certain advantages of using implicit representation, and there are certain disadvantages, just as we had looked at in the cases of curves, right. So for instance, if I want to find out whether a particular point lies on a surface or not, through implicit surface, it's very straightforward, it's easy. Whereas in the case of parametric surface, it's not that easy, right. So those advantages and disadvantages carry forward even in the case of surfaces, right. So we are basically going to look at the parametric surfaces, and just the way we had seen the parametric curves, we would like to actually extend some of the notions what we have studied in curves, right. So before we actually see similar constructions, for instance as Bezier curves or B splines, I would like to look at some of the parametric surfaces which are simple to construct and you must be very familiar to them, right. So, for instance, the construction of surfaces using revolution, right, rotation. So, what do we have? So, it is one of the simplest way to generate surfaces, right. We have a two dimensional primitive or an entity defined, which you rotate about an axis. Okay. So, for instance, if you have just a point lying here in x y plane and you rotate that point about x axis, you get a circle, right. Similarly, if I just take a line defined in x y plane, I rotate that line about x axis, I get a cylinder, right. So, these are very simple ways to have these surfaces constructed, and through the construction we also observe that if I take a cross section of the surface which is constructed using this method, that is going to be a circle, right. If I take a cross section perpendicular to the axis of rotation, that cross section is going to be a circle, right. So, this line here is some sort of a generating curve for the surface of revolution which we are constructing, right. So, now looking in parametric form this construction, what we are saying is that if I have the parametric equation of the entity which is to be rotated, that could be defined something like the way we had seen parametric curves, right. P t defined in terms of x t, y t, z t, right. And then you have a rotation of that entity. So, that gives you the second parameter for the definition of the surface. So, in a way we form a biparametric function which gives the surface, right, of t and phi, right. So, an example is that if I rotate something about x axis which lies in x y plane, right, then the biparametric function of the surface which is constructed can be given as x t, y t cos phi, y t sin phi, right. So, it is a biparametric function in t and phi, right. So, I can get any point using the parameter t and phi on that surface, right. Okay. So, looking at some examples, right. So, I can actually construct a sphere by rotating a semicircle centered at the origin and lying in x y plane, right. So, if I look at the definition of the circle in parametric form, the parameter which is being used here is theta, is given as x r cos theta, y r sin theta, right. And when I apply the biparametric function which is the rotation by an angle phi about x axis, I would get this, right. So, it is a biparametric equation with the parameters are theta and phi, right. So, with proper range of theta and phi, I can construct the sphere. right. So, similarly I can also construct shapes like ellipsoid, right, by rotating a semi ellipse about x axis, right. Okay. I can also construct a torus, right. So, there if I rotate a circle which is lying in x y plane and whose center is not at the origin, right. So, there is an offset from the origin of the center of the circle, right. So, if I rotate the circle about x axis, I again get the surface which is torus, right. So, in fact, we can represent the circle again in a parametric form with an offset h and k. So, h and k is the location of the center in x y plane, and by again using biparametric function in theta and phi, we can construct the surface, right. So, these are some of the ways you are very familiar how to construct these surfaces. So, now if you want to represent this construction in a matrix form, then all you are doing, if I have a point located in x y plane, if I have a point located in x y plane, let us say a point x y, then the rotation about x axis causes this point to have the coordinates like x y cos phi, y sin phi, right. So, through this transformation I can observe the matrix which causes this transformation, and the matrix is this, right. So, you observe that a general rotation about x axis, if you recall the form of that, is very similar, except that the fact we are using the point lying in x y plane does not require us to have the terms here, right. So, this is the matrix which is causing this transformation. So, I can represent now the surface using matrix. Now, if you recall, a parametric curve P t can also be represented in matrix form, where I have these f which are nothing but some sort of blending functions, right, where I can also construct those in the form of a monomial polynomials, right, 1 t, t square, t q, and the associated coefficients, and some information of geometry which is g, right. So, we can also see these curves represented in matrix form. Now, when I am generating the surface of revolution using this parametric curve, all I need to do is use this matrix and multiply them, right. So, this gives me the surface q t phi in matrix form, right. Now, so far what we have seen is rotation about x axis, most of the example what we have observed, but that does not have to be the case. You can also construct a surface of revolution about using rotation about any arbitrary axis, and you know how to do that, right. So, this matrix H which is being used here will be some other matrix which would cause the rotation about an arbitrary axis, right. And once again, the parametric curve P t could also be any one of those parametric curves which you have studied, right. So, for instance, if you are trying to construct some sort of a wine glass, you may actually construct the silhouette like a spline curve, right, and do a rotation about an axis, right. So, now we look at other ways of constructing surfaces which are also parametric surfaces, which are the sweep surfaces, right. So, what are we trying to see here is that there is some parametric curve and we apply a transformation of that curve, right. That is what a surface of revolution is, right. Similarly, here in sweep surfaces we have some transformation which is causing the sweep of some parametric entity, right. So, here we sweep the curve, which means traversing of an entity along a path, right. So, again I can represent the generated surface as a biparametric function using the parameter t and s, where I have the curve or an entity defined through p t, and this is what is causing the sweep, right, T s, that is the sweep transformation, right. So, one of the simpler transformation which you can see and construct surfaces is that if I use a translation sweep of a circle, then it can generate a cylinder, right. So, what I have is this is my parametric curve P t, and I am causing a transformation like a translation of this along some path or along some axis, right. So, this gives me cylinder. If I use translation sweep accompanied with scaling, then I can generate frustums or cones of frustums, right. And if I let us say add a rotational transformation, I can generate things like helix, right, twisted elements, right. So, all we are doing is taking some sort of a contour which is defined through P t and performing a traversal of that through a trajectory, right, and that trajectory may be generated using transformations like translation or rotation, right, and we may also cause transformation of the contour itself, which is scaling or any other transformation, right. So, generalized cylinders can also be generated using a similar process. Rotation is a special class of?
It's a subpart of sweeping, because for example, in the first case also we, with a circle not rotating about the center, about its center, we generated an helix.
Right. So, surface of revolution can be considered as a special case also, that is what you are saying? Yeah, that is correct. So, that is also a sort of a sweep process, right. Okay. So, next, so these are the surfaces which you are very familiar with and involves a very simple method of generating them, right. So, now just to see it another example, I could also use P t as some spline or any other parametric curve. So, for instance, let us say if I have some cubic spline defined in xy plane, and if I use a translation sweep, then again I can use the matrix form of the transformation, right. So, again I can have the sweep surfaces in matrix form, right. So, this is the translation factor I have, and I can use some sort of a resolution definition of the translation which I am causing. So, each of these translated curves could be the unit resolution I am causing the translation with. So, n could be some number, and s is the amount of translation you are doing in at one instance, right. So, you can generate surfaces like that. Now, when you have these sweep surfaces generated, though we have not really looked at the methods of shading and rendering, but there is an issue for what normal you would like to use for the purpose of rendering. So, let us say I have a contour or a polygon which is the contour for generating the sweep surface along a certain path, right. So, I am basically doing a traversal of this polygon along this curve, right, and in some way I will be rendering these polygons, right. Now, the question comes, or I will be rendering the points on these polygons. The question comes that the normal of this contour or the polygon, either I can use some fixed normal which is the normal of the contour at the beginning, right, and then display this surface, right, for the various points I have, or I can also use some transformation of the normal, right, which gives me the normal as a tangent to the curve along which I am traversing, right, and that might be a better way of obtaining the surface to be displayed, right. So, this is more of a display issue of the surface which is constructed. So, you are trying to align the normal of the contour with respect to the tangent of the trajectory you are using. Makes more sense, right. Okay. So, now so these are, let us say, the two kinds of surfaces which are very simple to generate just using a contour information and some transformation to those contours. Now, let us go back and see the methods which are in some way extension of what we have seen as the parametric curves, right. Okay. So, one of the simplest way of defining surfaces is bilinear interpolation. Just the way we have linear interpolation to be the simplest way to get the curve between two endpoints. For instance, I have a point P1, I have a point P2, then the simplest connection or a curve I can obtain between P1 and P2 is this line, right, which is obtained through linear interpolation between these 2 points. In a similar way, I have a simplest surface construction which is obtained using bilinear interpolation of the 4 corner points. So, what is the problem here which is being posed? That given 4 points B 0 0 B01, B11 and B10, right, what is the simplest surface which interpolates these 4 points? Okay, that is what we are trying to construct. So, just the way we had done the linear interpolation between 2 endpoints, right, we can do a similar thing to construct a surface which would interpolate these 4 points. Right. So, if I consider, let us say, some parametric domain as u v, a rectilinear parametric domain, then I can use the same concept as linear interpolation and generate a bilinear surface, right, which is to say that I have some 2 stage interpolation process, right. So, I can decompose the problem of 2 pass linear interpolation, right. So, I have these 4 points. Now, what I do is, as far as the boundary of the surface is concerned, that is a simple linear interpolation between the points, right. Now, for any point, the internal point of this surface, what I can do is I can use a 2 pass linear interpolation. So, the first pass enables me to get a point here, right, which is the linear interpolation between B 00 and B 01, right, between B 00 and B 01, right. And similarly, I would get a point here which is a linear interpolation between B 10 and B 11. Right. So, I get some point here which I represent as B 010, which is nothing but the linear interpolation of B 10 and B 11. Now, what do? I apply again a linear interpolation now in u, the other parameter, right, and I obtain this point, right, and that is the point on the surface. Right. So, this is the surface if I represent as x u v, this is nothing but now the linear interpolation of these resulting points, right. And again I can write this as in some vectors and matrices, right, and have 1 minus u u, and these are nothing but the geometric information, which is nothing but the 4 corner points I have, and the other polynomials, in this case they happen to be just a linear function 1 minus v and v, and I can write again the surface x u v as some sort of a functions b i's and b j's along with the geometric information using b I j, right. So, the surface which I obtain is a simple surface which interpolates all these 4 points. Now, if you observe the isoparametric curve or lines, what do I mean by isoparametric curve or line? A curve which has the same value of say u or v, right. So, if I go from here to here, so if I have, let us say, v is equal to constant, right, then the line which I get here is, or the curve which I get here is a line. Similarly, if I use u is equal to some constant value, the curve which I have is a line, right. But the curves, let us say for u is equal to v, is not a line, right, because this is going to be then a quadratic function, right. Remember that these points are in space, right, these are not points in a plane, fine. Okay. So, this is the way I can construct a bilinear surface which interpolates the 4 corner points, right, just a straightforward extension of linear interpolation. Now, let us say I extend the problem. So, what was the problem posed in the bilinear interpolation? That I was given 4 corner points and I wanted to obtain the surface interpolating those 4 corner points, right. Now, what do I have? The problem here is that I am given 2 curves, space curves C1 and C2, right, and I want to construct a surface which has the boundary as these 2 curves, right. So, in other words, if I represent my surface as, let us say, x u v, right, then the boundary corresponding to v is equal to 0, right, which is nothing but x u 0, is the curve given to me as C1, right, and similarly the boundary corresponding to v is equal to 1 is given as C2, right. So, apparently there are several ways you can do it. So, what is the simplest way you can think about? You understood the problem, right. These are the 2 curves given to you, these are space curves, and you want to construct a surface which has these 2 curves as the boundary curves.
So, trace it point by point, take a point, start from the left extreme for both the lines,
right,
and keep moving along the curve. Say if when you're tracing the curve you had some parametric definition of the line or something,
right.
so you pick those points, then do bilinear for those, move ahead, do bilinear again, and so on till you reach the right extreme.
Bilinear,
Similar to
Okay.
what
huh?
Linear
Linear transformation of C1 and C2. Okay. So, what is being suggested here is that if I take a point here, right, and perhaps take a point here for the same length of the parameter and join them by line, right. Then I go to the next point on this curve for the same parameter t, and I go there, the other boundary, join by them by line, right. So, it is in a way that if I have some kind of a ruler, right, I just connect by these 2 points through a ruler, right, ruler being the line here, right. So, that is what is being done here, and that is why we call the surface which is generated as a ruled surface, right. So, all I am doing here is take this point, connect to the other point of the boundary. So, it is just a traversal along the boundary curves or the contours and connect the points for the same parameter value, right, which in turn means that I do a linear interpolation of the contours C1 and C2 in V, right. If I have these contours defined as C1 u and C2 u, right. So, now again if I look at the isoparametric curve for constant u, it is just a line. Right. So, that is the simplest way of constructing a surface which interpolates the curve C 1 and C 2. Fine. Okay. Now, I further change the problem. Okay. Let us say, so what did I have in the previous example? That I had only two boundary curves, right, corresponding to the surface which I wanted to generate. Now, let us say I have now four boundary curves, C 1, C 2 and D 1, D 2. So, in other words, I have the surface or the boundary curve corresponding to v is equal to 0 as C 1 u, for v is equal to 1 as C 2 u, for u is equal to 0 as D 1 v, right, and u is equal to 1 as D 2 v. So, these are the four boundary curves I am given, and the question we have is, we want to construct a surface which interpolates these boundary curves. That is, the boundary of the surface which I construct should have these as the boundary curves, right. So, the problem is clear. So, how can we do that? Any suggestions? What is it that comes to you first in your mind? Okay, so let's try to see if we can do something using ruled surfaces, right. So, let us say if I construct a ruled surface between C 1 u and C 2 u, right. This I can do it, I know how to do it. I just construct this ruled surface between C 1 and C 2. Then I construct another ruled surface between D 1 and D 2, right. Now, can I do something?
So, the point of intersection of the corresponding ruled lines, we can take those points, and that
Point of intersection of the contours or these lines,
corresponding ones.
these lines and these lines. So, you are suggesting that those points are on the surface, something like that? See, it sort of gives you some partial result, right? Something missing. Okay, let us say now the fact that I have generated this, the fact I have generated the other ruled surface, what happens if I just add them?
Places where there will be lines where you don't need lines, and places where you need lines where there won't be lines.
Okay. So, let us see what do we get if I just sum them up, just add these two, and then maybe we can do something which is extra, right. So, I add these two, okay. I get something like this. So, once again do not take this as a exact form of the surface, it is done by hand, right. So, what do I have? See, through this ruled surface R C, I was able to satisfy the constraint for the boundary curve as C 1 and C 2. Right. Similarly, I was able to satisfy here while using R d, the rule surface between D 1 and D 2 for these curves. Right. But as a consequence of adding them, I am getting something extra here. Right. I am getting these lines in addition to this curve. Right. This is what is happening. Similarly, these lines in addition to this curve. Right. Now, the question is, can I do something to get rid of the extra which I have? See, clearly I have something extra, isn't it? The addition gives me something extra. Now, is there a way I can get rid of that extra thing? So, see, the extra things are these line things, right? Where do you get lines? When do you get lines? Okay. So, we have seen the bilinear surfaces, right? What are bilinear surfaces? They actually connect these points through lines, these points through lines, right. So, isoparametric curves for a given value of u and a given value of v are lines, right. That is what you have the extra thing. Right. So, if I subtract this from the sum which I have done for the two ruled surfaces, I will get what I want. Right. So, what I am saying here is that I have the ruled surface which is obtained through C 1 and C 2, let us say I call it R c. This is another ruled surface which is obtained for the boundary curves D 1 and D 2, which is R d, and this is what I have is the bilinear surface for the four corner points, which I call it as R c d. So, the Kuhn patch is due to Kuhn, that is why it is called Kuhn's patch, is the resulting surface which interpolates the four boundary curves and which is obtained as the sum operation of the ruled surfaces R c and R d minus the bilinear surface. Okay. So, mathematically if I want to write this, so R c u v is nothing but which is obtained as the linear interpolation of the boundary curves C 1 and C 2, which are nothing but x u 0 and x u 1. Similarly, R d u v, which is the other ruled surface obtained from the linear interpolation of the other boundary curves, right, and R c d is nothing but the bilinear surface, which we have also seen, right. Then the resulting surface, which is x u v, is nothing but R c plus R d minus R c d, which I have just substituted for each of these terms and got this. right. So, now in fact, if you observe, these are the sort of the blending functions which are being used here, 1 minus u and u, 1 minus v and v, right. So, one can even think of having some generalized form of this Coon's patch, where I can define 1 minus u as some function as f 1 u, right, and u as some f 2 u. Similarly, 1 minus v as g 1 v and v as g 2 v, and I can use then f 1, f 2, g 1, g 2 as the blending functions, right. So, what we have seen is that how do we obtain the interpolating surface for various scenarios, right. The bilinear surface is obtained as an interpolating surface for 4 corner points given. Ruled surfaces are simplest form of surfaces for obtaining surface interpolating 2 boundary curves, right, and Coon's patches are the surfaces for obtaining the surfaces for 4 boundary curves, right. And we can see that they can be represented in a very similar way as what we observed in the case of parametric curves, right. So, next time what we will do, we will talk about, for instance, surfaces which are extension from Bezier curves. So, Bezier surfaces. Similarly, surfaces which are extension from B-splines. So, B-spline surfaces and so on. Okay. So, let us stop here. Thank you.